Now that we've gone through all of our operations with our radical expressions, we're going to talk about the last one, which is called rationalizing denominators. And this is essentially how we do division of rational expressions. Just like when we simplify fractions such as 2/4 or 3/6, we always reduce them into lowest terms. That's how we always simplify our fractions, and it's implied at this point in this level of mathematics. Just like with simplifying fractions, rationalizing denominators is also going to be a required step in order to consider the fraction in simplest terms. Now, we can also rationalize the numerator, but that's rarely a process that's ever done. We always consider the fraction simplified if the denominator is rationalized, which means that any radicals are confined to only the numerator, and there's no radicals in the denominator. Up until now, we've been able to use quotient rule to simplify our fractions, and we haven't ended up with any radicals in the denominators. Now we're going to have to take that a step further. This process always involves multiplying by some quotient in the form of 1 that allows us to eliminate the radical. And usually that idea is done by taking the radical expression in the denominator and considering what radical can I multiply it by, so that I end up getting something I can take the root of. And then whatever I multiply on the bottom, I'll end up multiplying on the top. So here we see we have the square root of 2 in our denominator. Well, in order to take the root of whatever this radical is, if I multiply 2 by 2, it ends up giving me a perfect square. Square root of 2 times the square root of 2 gives me square root of 4, and then we multiply the numerator as well. This allows me to simplify this denominator to a rational number, giving us a rationalized denominator. And so the simplified version of this radical is the square root of 6 over the square root of 2. This process is going to be pretty straightforward for most of the examples. A lot of times we end up just multiplying by the denominator itself. So in this case, we'll multiply by the square root of 5 so that we get the square root of 5 squared, or the square root of 25, and then when we rationalize it, we end up with a rational denominator of 5. However, sometimes we'll have slightly more complex radical denominators. Here we have 9x. 9 I can already take the square root of, but I can't take the square root of x. So we'll still need to rationalize it. And in order to take the square root of x, we need to multiply it by another square root of x. This gives us 2/16x in the numerator, and then we have the square root of 9x squared in the denominator. We can simplify both the numerator and denominator now. 2 times 4 times root x over 3x. This gives us 8 root x over 3x. Now our fraction is rationalized. If we consider a cube root, we now want to figure out what can I multiply this denominator by to get a perfect cube. So we can go ahead and simplify our numerator using our quotient rule to split these apart. And then we're going to want to multiply and turn this 2 into a perfect cube. We can do the cube root of 4. That gives us 1 cube root of 4 over the cube root of 8. 8's a perfect cube, so we can take that cube root. We can also consider this, instead of saying the cube root of 4, we consider, well, I have 2. I end up needing 2 to the third power so the radicals can simplify. So another way that we can approach it is we can multiply by the cube root of 2 squared. That will give us the cube root of 2 to the third, allowing us to eliminate that radical. Either approach is fine. Depending on the number you have, it might be easier to consider taking that number squared to get the cube root. Again, we can apply our quotient rule to split these into 2 separate radicals. I want to be able to square 3 and y, so the square root of 3y. When we multiply our numerators, we get 21xy. In our denominator, when we have the square root of 3y squared, it leaves us with a denominator of 3y. Now we'll take a look at our fourth root. 81 we can take the fourth root of, so we don't need to do anything there, but y to the fifth we can't. So we need to take this fifth power and turn it into something larger that we can then divide by 4. So if we multiply it by the fourth root of y to the third, then these will combine to give me y to the eighth. So we'll multiply both top and bottom by fourth root of y to the third. This leaves us with fourth root of x, y to the third in the numerator. Then we have 81y to the eighth in the denominator. The fourth root of 81 is 3, and then fourth root of y to the eighth is y squared. Same here, we can go ahead and take the cube root of 27, but I can't do the cube root of x to the fourth. So if we multiply by the cube root of x squared, that gives us x to the sixth, where we can take the cube root. Numerator, z squared x squared, and our denominator, 27x to the sixth. Numerator stays the same, and the denominator becomes 3x squared. So throughout this process, we just want to focus on what can I multiply my denominator by so that I end up taking either the square root, cube root, or whatever index we have for the denominator, so we leave it as a rational expression. Now this process only applies when we have a monomial term in our denominator. In the next section, we'll talk about what happens if we have two terms in our denominator with a radical expression.